Yeah, hello. Yeah,
Yeah,
I
very good
see Dr.
afternoon.
Dr. Srinivas has joined us. So, yeah, good afternoon, all of you.
Very
Uh,
good afternoon.
I don't know whether the Professor Srinagesh is still there. Yeah, if Professor Srinagesh is not there, then I would very, quickly introduce our next speaker, Dr. B. Srinivas. He is the Senior Assistant Professor at Department of Applied Geochemistry, University College of Science, and he has served at many, administrative positions, uh, uh, starting right from, we were both together as wardens, and also he has served in the examination branch as one of the uh, additional controllers, and presently he is heading the department of applied geochemistry. He is known for his, research in applied geochemistry. He has executed many research projects, and many students have still now got their PhDs in applied geochemistry under his guidance. A great friend of mine, Dr. Srinivas, also deals with kind of, teaching at the PG level about different research methodologies. And today, I think he's going to share with us his ideas and his understanding about different types of research models as such. So, with this brief introduction, I'm happy on behalf of the UGC-HRDC Osmania University, on behalf of Osmania University, and also on my personal behalf, I welcome Professor B. Srinivas to deliver his talk.
Yeah,
Dr.
very good afternoon. Yeah. Thank you, Dr. Srinivas. Thank you very much for your nice words. Good afternoon, very participants. It's indeed a great occasion to meet many of you here. Uh, like I'm working from the university. Mm, I've been told that I have to talk to you about research models. For that, I would like to present something. Is there anyone from earth science background? If then, that would be really good. If not, so also it's really great.
Sir, sir. Mostly our participants are lecturers from the government degree college, and most of them are from the life sciences, mathematics, computer science, physics, and chemistry.
Okay.
Unfortunately, we don't have anybody from earth
Still,
sciences, but
still it's great,
yeah,
really
but
great.
yeah, but I think that, because we are talking about research models and all those things, and
Yeah.
also keeping in view the national education policy that encourages the interdisciplinary courseworks and all those things in
Yeah.
future.
Yeah.
If
Yeah.
any
Yeah.
student in any student wants to do some kind of, earth science research also, our teachers would be ready, in
Yeah.
fact. So
Yeah.
yeah, thank
Yeah.
you very
Thank
much,
you.
sir. Please
Yeah.
go ahead.
Thank you. Yeah. If there is no art science student, also it's really great, wonderful. It is not compulsory that I want to speak to some art scientist or something like that. It's really great that we have some different backgrounds, all the participants. I would like to just talk to you about some research, then we'll come to about research models. Uh, I don't know if I can share you the slides. I'll try to share you if it is okay. Uh, um, yeah. Where is it present now? Then I have to go to a window. Yeah. Uh, yeah, I think it's visible now.
Yes, sir.
Yeah, thank you. Yeah, I'm just trying to show you some slides. Then maybe I'll talk to you about these things. Maybe I'll make it full screen. Yeah, it's visible now.
Yes, sir. Yeah. Are you in the presentation mode? Yes. Now it
Yeah,
is visible. Yeah.
yeah. Uh, yeah, the that is what is I just came to know that this short-term program is about research process and research design in sciences. It's absolutely sounding great. Research, I like. I don't know, like when students come to me, they talk about PhD and other things. They come and they finish off and they finally they get awarded. They're so happy and they try to be very happy, saying that, sir, we have completed PhD now. We are. Then I say, you are a doctor now, doctor so and so. So then what happens? Then I'll tell them, now this PhD is not that you have achieved something. It is only the first step. That is, you have taken a admission into research process. It is not that PhD means you have finished research. PhD means really means you have just started doing research. PhD means you just started understanding what is research. That is what I constantly tell my students who have completed PhD. And for that matter, not only my students, whoever comes and tells me that he has completed his Viva and all that. And many times we'll be conducting Viva as an internal member or an external member or something. The final word I tell you very often is PhD is not like it's an end process. It is, that is what I say, it is a starting process for researchers. Of course, there are many people who believe that PhD is only to get some job or to get some increment or do something. For them, it is okay. But for otherwise, PhD is only a starting point of the research. So we'll just talk about what is research, and then we'll talk about some research models as such. That is what I'm going to talk about. Now, what is research? Many people say it is need not that a PG student has to talk about research. It's a research has become a colloquial word nowadays. Like if you're talking some things, I think many of you are from Telugu background. I can talk some words in Telugu so that the conversation becomes very lively. If you talk something about research, they say, oh, you have done a lot of research on this issue. Oh, Pakistan issue. Oh, you have done a lot of research. Only if you talk about something, you talk about national education policy, then oh, you have done a lot of research on national education policy. That research has become a colloquial word these days. That is to study in depth. That is what is called as research. In-depth study of that particular topic or subject is what is the meaning of research that is being understood by any person these days. Like maybe it is from a science background, arts background, humanities background, any background, MBA background. It is like an idea which has to be pursued, and more things, more details have to be known. That is what is called as a research. Of course, what is that is you are going beyond personal experience. Means like whatever you know, from there you start knowing more and more. That is what is called as research from different sources. Maybe like you want to know about the GDP of a country. Then what do you know? First you'll know what is GDP. Then what is that? All that. Suppose if you want to know about now coronavirus, then first you'll start knowing about what is virus, then what is the coronavirus, what is COVID, how does it spread, all that. These days everyone is a expert in corona. They talk lots of things because we are getting so much of information. That is what is called as sources. Earlier we never knew what it was, but we know many things. That is what is called as many sources. That is WhatsApp information, paper information, TV information, all this, Google information, all these informations. Okay, so this is all beyond our personal knowledge and research experience. So what is it? To explore an idea. You get an idea, like I want to know something about this. That is what is an idea. Like if you want to say you want to know more about a virus, or you want to know what is a gold deposit, or you want to know like a particular species of a plant, how does it survive in different climatic conditions. That is what's an idea. Then issue, how does it happen? Then you solve them. That is what is called as a research. Then you see there are you see when I talk or anyone talks, it's all on paper, like types of research: descriptive, analytical, or is it applied or fundamental, it is quantitative or qualitative, it is conceptual or empirical, some other types. Like I say, it's only on paper, but strictly if you just start doing research, you will not just stop there, like I'm only doing descriptive research, I don't want to do analytical research. You can't say that. And without your knowledge, it goes on from one type to another type. all that. Suppose if I talk of applied research and fundamental research, like if I specify some earth science example specially, maybe research I cannot talk more about other subjects. Suppose if you talk about fundamental research means, like if you talk only about rocks, the minerals, where they apply, how they are formed, all that is fundamental. Applied means something which is very relevant to society. Society means like if there is more of fluoride, where does it come from? Is it there in the rocks, or is it there in the soil, or is it there only in the water? Then how has it spread? Showing all these things is applied research. So applied research has got more of relevance to the society than fundamental research. Okay, I don't say that you have to do only applied research. Fundamental research is also equally important, because without fundamental research you cannot apply those fundamentals to the society. So this is how research develops. Of course, when you talk of a PhD or when you talk of a project, you have to be very clear whether it's a fundamental or applied research, because these days the funding agencies are asking what type of a research you want to do, all that. So you have to be a bit clear whether it's applied research or a basic or fundamental research. No, nowadays, all of you know, because of the new national educational policy, everything is interrelated. You can do anything now. So we have lots of sciences like physics, there, chemistry, astronomy, earth sciences. Okay, then life sciences, both botany or zoology or biology together. So we have lots of science. So how to do? We have to look like for a method which contains all these things. Then we start talking about these things. No, I don't have to tell you what is physics or what is chemistry or what is biology. So you see, that is what I can tell you. Basic sciences are also called as pure sciences or natural sciences. Then we have some applied sciences. Okay, so physics, you know, like examples include physics, mathematics, biology. Applied sciences are also called practical sciences. Okay, then there's, for instance, engineering is an applied science, because all the physical like formulas or physics, the applications of physics are there in engineering. Maybe it is electronics, or maybe it is mechanical, maybe it is computer science. Engineering is a part of physics and chemistry, all these things. The applications of all these things is engineering. So engineering, especially we talk about applied science, but whereas the other parts, physics, chemistry, other things, they are all the basic sciences. So either biology or all these things are basic sciences. So basic science is like what we do, try to do. That is why we say professional. Professional means what? Professional is nothing but the application of basic science or basic knowledge is called as professional. Those are called professional courses. Engineering is a professional course. Medicine is a professional course. So why we say it is a professional course? Because the applications of these sciences is called as a professional course. So that is how we talk about. Then what is scientific research? Then we have to build so many theories. What are those theories? Like we build, for example, if you want to know something, how was Earth? How was Earth? We know all that Earth was formed 4.6 billion years back. So how it was done? Based on so many theories. How the plants were formed. When plants were formed, Earth was only formed, or other plants were also formed. So these are all called theories. These are all called concepts otherwise. So these concepts, what we do here is we try to establish a relationship between all these concepts, theoretical concepts, then the relationship, then we observe very closely how it is done. So this is what is called as a scientific research. So all these things is being going on since long time, since time immemorial. Before people wanted to know what is physics or what is chemistry or what is biology. Today we are going into many specialized areas, like in suppose earlier we had only geology. Now we have geophysics. Now we have applied geochemistry. Like this, each branch, like I don't know, I know, like in botany also we have got viral, like zoology we have got virology, wildlife. Different fields are there. For each science there is a different field. Why? Because a lot of research is going on. Every person, like he wants to get into a specific field to do his research and to make things very interesting for him. Like if you want to do something, you go and you want to go to do some research. Is I told you PhD is the first point. So what you do, you go to some person, then you talk to him, you try to know what he is doing. Then if you have some idea, then you talk about your idea to him. then you find out mutual consent, mutual interest, then you start doing. That is, first you should have an idea. That is what is called as a research. Now, to have an idea, you have to read a lot. You have to read all the theories. Then once you are well versed about these theories, then you have understood all these theories, what has already happened, how we got this present state. That how do we know this? By reading the theories what have been proposed, by reading the concept what have been proposed. Then we get an idea that leads to what is called as scientific research. Now, without reading, without doing anything, then it's very difficult for us to continue research or start research. First thing is, to do any research, we have to know what has already been done, at least to some extent, if not to full extent, what has already been done in what you are proposing to do. Then only you can start the scientific research. So now you see, that is what I tell you, depending on research training interest, the scientific inquiry starts. That is inductive or deductive. Inductive is a goal. The goal of a research is to infer theoretical concepts, that is from the observed data. In deductive research, what happens here is to test the concepts. Like if I say Earth did not have atmosphere when it was formed, that is what is called as deductive. How we know? Because we have studied the same concept we are applying to other planets. That is what we say. So there's a concept that there was no atmosphere when Earth was formed. So we know there are other planets also where there is no atmosphere. So that is how we say this concept is correct. So this is how we talked about the theory using new empirical data. Once we start doing that, this is called as theory building research, and deductive research is theory testing. Okay, so this is how we start about. Then there is something called a research cycle. What is that research cycle is? I'll just show you. What is that research cycle is? And I'll just show you. That is what, again, theory building and theory testing. That is, somebody has proposed a theory, you can test it. That is also research. Then once you test it, if the theory is okay, it's okay. If it is wrong also, you can say it is wrong. Either way, it is a research. Again, there is some notion that like if I talk about exploration for gold, someone is looking to find out whether gold is available or not at a particular place. Then if it is there, it is a research. If it is not there also, it is a research, because you are saying it is not there. So either way, it is a research, but you have to be very strong. We have to deduce why it is not there. What made the rocks gold not available there? That is what is called as deductive research. So you have to be very careful in theory. Theory is like you can test any theory, then you can do all these things. So this is what is called as both kinds. Now, it requires both skills, theoretical and methodological skills. You have to have that skill, know how. That is, you have to look at various disciplines across. Then you have to know what is happening. Suppose you talk about physics, then you should also know what's happening in chemistry, because both go parallel. Suppose I am doing research in geology, I should know what's happening in physics and chemistry also, because each of the science is interdependent. Without knowing all these things, I'm not saying that you have to master all the other sciences. You have to know what's happening there, what's really happening there. Then you can do your research better if you have a cross-discipline knowledge. That is very, very important. Okay, then it is really very hard to master everything. All the skills you cannot master. So you have to only observe. Then you can talk to your peers, you can talk to the subject experts and do all these things. You see, we have lots of scientists very well known: Galileo, Newton, Einstein, Niels Bohr, Adam Smith, Charles Darwin. So what did they do? They are all master theoreticians. They have proposed many theories. And most of them did not have very basic education, like they did not have PG, post-graduation. They are not serious researchers. But many of them were highly successful because they postulated many theories which are very well known today. Okay, we know what is Newton's theory, what is Galileo's theory, what is Einstein's theory, what is Bohr's theory. I'm not saying that all were not highly educated. I mean, most of them are highly educated. Few of them were not educated also. They had some basic knowledge of science. Okay, so with this, I'll just talk about this very interesting aspect. When you talk about research, you have to be very careful about replicability and precision. These two are very, very, very important. Once you know understand what is replicability and what is precision, then you can be very. I'll just show you a model. Then yeah, I don't know. Yeah, this is what I wanted to show. If you just see this diagram, the very first one is reliable and valid. Second is valid but not reliable. Third is reliable but not valid. The figures themselves are very, very illustrative. Like it's like a bullseye. You talk about rifle shooting. So what's happening in the first scene? All the bullets have hit the target. In the second one, all are spread over. In the third one, what's happening? All the bullets are spread over some point, but they are not hitting the target. You see, first one is reliable and valid because whatever you have done, it is reliable because you are getting the same result every time. When you get the same result every one, you say it is reliable. If you are getting this correct result, it is called valid. Same result is called reliable. Correct result is called valid. The second one, you see, your result is neither reliable nor valid. Why? Because each time you are doing, you are getting a different result, but it is not valid. Many times, some of the values are correct, some of the values are wrong. So that is what we say. Okay, some results are valid, so but still you can say valid but not reliable. The third one, you see, it's absolutely like you're getting exactly the same result every time, but it is never closer to the truth, never closer to be correct answer. That is called, it is validity is lost. There is no validity, but it is reliable because you are doing the same mistake again and again and again. What mistake you don't know, but you are sincerely putting your effort. So you are getting reliable but not valid result. So this is what I wanted to talk about. So this is what I was just talking to you. This is scientific method, replicability and precision. These two are very, very important. Once you have understood what is this thing, then you talk thinking like a researcher. So whenever you're conducting any experiment, then you connect all these dots and get some value or result. So this is what you say. Then you get this. So you have to be always reliable and valid. If you are not doing this, then your research goes hayway. Hayway means you will not get a correct result. So now you see, what is the design of a research is, we have like many processes. One is the data collection process, the second is the instrument development process, the third is sampling process. Okay, 3 processes are there. Data collection is, of course, how do you collect data? Like you have previous literature. Maybe in our days when we did, there was no internet, so we had to depend going to library, and maybe we had to collect the like journals. Maybe photocopy it. Photocopying was also difficult. We used to write in the books like some points and all those things, whatever is the data collection is a big issue those times. Nowadays data collection is not so big thing. Now you can, if you have an internet, you can somehow get all the data. That is a bit easy now. The instrument, okay, the science, we need lots of instrument to do some research. In social sciences and arts, we don't need any instrument, but especially in sciences, you need a microscope or you need some chemicals, you need some instrument to do some analysis, all that. Then maybe you have to collect some sample process. Like in geology, you have to collect some rock samples. In botany, you have to collect some plants or plant species or some species. Then in zoology, you may have to collect some other samples. This is how you start collecting samples. Then we talk about so many things. Just excuse me, there's someone here. Yeah, sorry for the disturbance. That is what you see, reliability and validity. I told you, reliability is a degree to which the measure of construct is consistent or dependable. You are dependable, then you say it is reliable. But reliability does not mean that you are always correct. Okay, correct is the reliability is only dependability. How far we can depend on you. So reliability is, that is very, very, in other words, it is if we use the scale to measure the same construct multiple times, you get the same result. That is what's happening. Okay. And then guessing technique for measurement is unreliable. That is, you see, a more reliable measurement may be to use a weight scale. So when you stand on a weight scale, you get the same weight again and again. If it is not zero corrected, what happens is many times the weight scale, it may be 5 or 10 kg more or less. It may be -5 or it may be +5. So when you stand on that weight scale, you're getting same result. That is called reliable. But is it valid? It is not valid because you have not corrected to zero. When before you standing, you should check whether it is showing zero or not. If you have not checked, that means the results are not valid. It's only reliable. The instrument is reliable, but the process what you have done is not correct. So it is not valid. That is what is reliability and validity and reliability. So this is what is a usually research cycle: learning, diagnosing, then action planning, action taking, evaluating. Then it's a cycle. It's not a one-time process. You may be stuck up at some place for some more time. At some places you may come out very fast. So a PhD does not mean that one cycle you may get PhD, but research is a cycle. It goes on and on and on and on. So that is what you talk. Now, what is modeling? I wanted to talk to you about modeling, my aspect today, because we have just talked something about the research and other things. What is model? We have been talking about models many times. As a kid also, we developed so many models. Like, by using paper, we made paper boats. What is a paper boat? It's a model of the original boat. So that is why we are interested in making a paper boat, because a model shows makes the person more interesting. You see, I don't know, like as a kid, we used to, whenever there were rains, there was water, we used to tear off those pages from the notebooks, make some paper boats and try to like float it on water. So what we were doing, it was only a model of what's happening outside. So knowingly or unknowingly, we were using models. Okay. Once you have become a teacher, you try to show some models to the students. Maybe now, like if you can, when I stop this video, you can see at the back of my chair, there is a globe model. Okay. So like if you want to show the students how the earth looks like, you take up a globe model, then you show this is how earth looks like. It is round, it is not totally round, but it's oblated, all that you try to show. Why? Because student or any person can understand better by looking at a model. So models are very important these days. So that is what you say. We have earlier, we did not have any Lego bricks or something of that kind. Those are called building blocks or Lego blocks. What we do, we try to use those small bricks or those small pieces, then try to make some kind of a model. Maybe it's a house or a space shuttle like this. You see, these are all different kinds of Lego bricks. Then you try to make a Lego space model. This is what is called as a model. So you have these different kinds of colors. This is a model, you see. So this is how the model started arriving, because a layman or is not even a layman, a child, an innocent child, like maybe if he's 4, 5, 6 years, he doesn't know what the space shuttle looks like. So looking at this, what you say, the booklet which is being supplied by these game makers, they can make different designs and different models. By that he can understand what is a space shuttle, what is a space model, all these things. So you see, these models are very, you say, I can say it is, they are imminent. Without models, survival is very difficult these days, because gone are all those days. Without models, we are not able to understand anything, everything and anything. Okay. So this is what is about the now. What there are many types of models, like physical, conceptual, mathematical. What is a physical model? Just now what I've shown you is making a space shuttle NASA, that is called as a physical model. Like if you want to know, like if you want to make a delta area, then what you do, you take a big cardboard. Then you see children these days, they do for science exhibition physical models. These are all called physical models. Maybe they try to make some physics students students who are interested in physics, they try to make some electrical circuits, then they show the bulb is lighting up, or they try to show some models. These are all called physical models. What you exactly make and show how it works. Maybe you take a cycle, then by just cycling it, you get some energy that is converted into electrical energy, all that. These are called all, these may be defined as physical models. Then you have some conceptual models that we'll try to speak of. Mathematical models means that you can deduce using some values. You put some values, you get some result. These are all called mathematical values. So most of the conceptual models are also dependent on mathematical values, except the physical one. Physical one is once you have prepared and you are just showing it. Okay, always physical models may not be possible to make. We cannot make all the physical models to show what's happening, because science has become so vast and there are so many variables that you cannot put all of them in physical models. Then we talk about conceptual models. These conceptual models use the base for conceptual model is the physical model. Then many mathematical values or variables are introduced in the physical models. Then you get a conceptual model. Then really it makes some sense what is a conceptual model. So this is what you say. Then that is what I told you. Like you make a delta area. Then what you do? You make a river. Then you make the water to flow. When water is flowing, there is some sediment. It gets deposited. So that you show this is a delta model. This is what is called as a physical model. Okay, so this is what you talk about the physical model. All these are physical. You can show as many as details as possible. Then if you are a chemistry person, we are talking about the atomic theory model. Earlier, you see, when we were kids, we hardly had any like atom. What is an atom? How does it look like? These are all difficult. But these days you have all physical models of all this, how an atom looks like. You can get different kinds of atom. You can make a water molecule. That is how it looks like. So this I'll just try to show. I don't know. There is one more figure. I'll try to show you that. No, this is what is called as a model. This is a scientific model. No, models are many things. Okay, physical models again. So then we talk about the biological processes. Then large scale structures are there. Delta is a big structure. Then you made it into a real system using a physical model. Then we talk about you see, we talk about, like, you see, when you want to make a model, yeah, that is what I wanted to show you. This is a Dalton model. And this is like what you can show what is happening. Like you say, this is one H2O, both H2 and oxygen. So this is how they are linked. So this is, you can show the students that this is what is, this is the benefit of science. Showing models, students can understand. Okay, how many links are there, how it is attached, physical. These are all physical models. So once you can show them the physical model, they'll be more interested. Now, before coming to that, I told you that modeling is very, very, very important. When I talk about modeling, it's really very important. How? I'll tell you. Suppose we are talking about earth sciences. I'll give you many examples of earth sciences. Now, you know, these days we are looking for oil. Where is oil found? Oil is found in sedimentary rocks. Many of us know. If you are not in a geological background also, you know oil is found in sedimentary rocks. Now, where are these sedimentary rocks? Sedimentary rocks are present everywhere. But what type of sedimentary rocks? And then how it is done? Now, for any sedimentary rocks, you have to have a reservoir. Then you have to have a reservoir. Then you have to have a cap rock. Then there should be sufficient oil. It should be migrating, and it should be stored. All these things make it an oil reservoir. Once you know what is a reservoir, what's happening here is, where do we have reservoirs? We have reservoirs at Bombay, especially. It's a big reservoir, cap rock. Then the Middle East is having a lot of oil reservoirs. Then nowadays, if you want to look for many oil, like if you want to explore about more about oil, what's happening in Krishna Godavari basin, that is, they are doing some reservoir modeling. How they do? Like, now this reservoir modeling needs lots of things, inputs. What are those inputs? First thing is, you have to know what are the rocks there. Then once you know what are the rocks there, then you can know what are, then you put it to a system. Okay, these days modeling you need is dedicated, like what you say, not a PC, a big system wherein you can feed in all this data, will get a model. A PC, high-end PC, maybe also do some most of the work. Okay, so reservoir model requires you should know what are the property, what are the rocks, what is properties, whether it is permeable, whether it is not only permeable, but whether it is porous or not, how whether it allows seepage or not, all that you have to know. Then we have to know about the hydrocarbon reservoirs, then fluid properties at depth. So you once you collect all this data one by one, one by one, then you feed into the many softwares are available. Of course, these days softwares are available to create a model. Without softwares, you cannot create a model these days. So once you get you get this data and feed into those the what I say the softwares, then what you will do, it will ask you so many variables, like what are the variables. So when you fill in all those variables, at last you'll get a beautiful model. Now, how worth is this model? That is one very important question. How worth is this model is, it all depends on two things. The person who has created the software, he should be going behind a reservoir model, how the oil is created, or how oil is created, or how oil is formed, and how it migrates, and all these things. Without knowing all these things, he cannot make a software. Maybe if that person can, that means it should have a combined effort of a computer person who can do programming, and a geophysicist or a geologist who has got a good information, so that both of them can interact and make a software programming, and make like a software tool to make a reservoir modeling. You see, so this, once a model is made, what's happening today, maybe today in 2020 you got a model, it's very good, excellent, many people have purchased. Maybe you create a software and sell it to maybe 10 lakhs, 20 lakhs, people will buy because the models are very important for hydrocarbon exploration, to find out petroleum, oil in many places. It's everything is okay, many companies may buy, and they may get they may find oil, and they become much more rich. But what's happening here is, at the end of the day, maybe 4 or 5 years later to this day, this model becomes obsolete. Means, why it becomes obsolete? Do you think that the oil where it is being found, the oil is gone or is evaporated? No, because there are some more variables that have to be added to this model to make this model more predictive. In the earlier versions, some variables might have been missed, but once you know this, some variables have been missed, then you have to add. Now, what is that? Like you say, supposing in reservoir, especially in oil models, what's happening here is depth. How, to what depth you can go? What is the fluid? What is the fluid rock interactions? All these things you have to add. Then, not only that, like what is the quantity of oil you get? That is also very important. Maybe how much you can drill, what is the quality, what is the quantity of oil you are getting, all these things are important. You see, then what you do, there is something called logging, well logging, seismic imaging, all this data has to be fed. Then you get seismic imaging is like geophysics plays a very important role in getting lot of the data for variables in reservoir modeling. Seismic data is very important. Once you get seismic data, that has to be fed into the reservoir modeling. Then geochemistry also plays a lot of model. What does it do is, you do some logging, you get some rock cores. When you get those rock cores, you'll try to know what are those rocks, whether it is sandstone, whether it is limestone, whether it is shale, all that. So you see, all this earth sciences itself has got so many branches, but you need so many experts to get the values of those variables. Once you get the values of those variables, it has to be fed into this software. Then you get what is called as reservoir model. So this is what is one kind of a reservoir model. These kinds of softwares are available. I mean to say that the modeling is not a physical model. It's a conceptual model. It's a mathematical model. So it all depends on the software. You have to create software, then you have to make a model, then you can run this model. So this is how it goes on. Creation of model is very, 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 very important. Unlike one, if you are successful in creating a good model, and if it is tested, it gives good result, then you become an expert. Then you are well sought after. So in research, what is happening, you see, these days, these models are very, very important. Without model, you are not a good scientist. This is very well known today, as of today. Why? Because in every subject you need a model to make people understand what's happening. Suppose if you talk about life sciences, agricultural sciences, we are talking about what do you say, the greenhouse gases, global warming. So carbon dioxide is increasing. All these things are happening. But for a layman, you make a model. Simple terms, I'll tell you. So what is happening today in India? We are a tropical climate. Okay, all the glaciers are there in the northern hemisphere and the southern hemisphere. What is called as there is an that is what is called ice line. Okay, above that there is a glacier. Then to tell a layman or to tell a non-science person what happens if the carbon dioxide content goes to, like, if it is 415 ppm now, if it goes to 450 ppm or 500 ppm, what happens here is, now the places where you are finding the glaciers or the ice now, those places will be similar to what is there in India now. So that is how we talk about. So those people, the places where there is ice now. Hello? Yeah? Hello? Hello? Yeah, there is some.
Mr. Chandraya?
Yeah, thank you.
He is muted, sir. Yeah. I think he is muted, sir. Yeah. Please go ahead.
Oh, thank you. Sorry, I thought I was just in a flow. I thought someone was asking something, so I just came back.
No.
Yeah, it's okay. Thank you. Yeah. I think it's visible now again. Yeah.
Yes, sir.
Yeah, I'm coming. There was sudden gap. Okay. So this is models are really very, very important. Without modeling, it's very difficult for us to talk about science. Why do these models become obsolete here is because the number of variables what we are thinking of today will definitely change over a couple of years now. So the models become obsolete every now and then because more variables have to be added. Once the variables are added, what happens? The model becomes obsolete. So you have to create more new models, or new softwares have to be purchased. All that's going to happen. Now, you see, that is one reservoir. You see, the reservoir modeling is, of course, a very important aspect. What I can talk about in earth sciences, not only in earth sciences but in other fields also. Definitely, there are models. Without this kind of models, it's very, especially so in earth sciences, because the data is so huge that human brain cannot pursue what's there, how the oil occurs and all things. So very important is you have to create a model. Without model, it's very, very, very difficult. You see, many recent discoveries, like you see diamonds. What does the diamond indicate? The diamond indicates what is there in the mantle deep inside, because diamonds come from deep inside. We'll try to know what is there deep inside. The diamonds tell us what is there deep inside. That is what is called as mantle petrology. Okay, like if you talk about nickel, it talks about large igneous provinces. All that is very important. So each of them talks about different things. So these minerals and other raw materials are also very, very important. Now, I'll try to talk to you about something called mineral. You see, these minerals or metals have been in use since long time, since time immemorial. We talked about the Iron Age, we talked about the Copper Age, then we talked about the Stone Age. Then what do you say? The gold, of course, gold has been there since some hundreds or thousands of years, people have been using gold as an ornament. Now, do you think that science was there at that time? There was no science. Without science also, people started exploring, exploiting these metals. Suppose if I say gold is like available
Hello?
in the purest form. That is what is called as gold nugget, or gold is available in a like in a ore where it has to be purified. So what's happened earlier was our ancestors, our great grandfathers were so intelligent and they were so knowledgeable that all those native gold, means which is the purest form of gold, was mined and was used. Not only the purest form of gold, but whatever gold what was appearing or what was there just shallow, that means on the ground or just below the ground, they have excavated. I'm talking only about gold. For that matter, for any metal, like if you talk about iron, you talk about copper, the most important metals which have been used since long time, they have been dug out and have been used. Okay, of course, in the last century when Britishers were ruling our country, they have exploited to the maximum extent all these metals, especially gold, copper, iron, all those things. Now, what's happening here is the surface bound metals and minerals have been exploited. That is why we don't have anything which is in the surface. We have to go deeper and deeper and deeper and deeper. If you are going deeper and deeper, we are not sure whether we will get any metal or not. For that we need what is called as a model. What is that model? We have to create a model and try to understand what's happening deep inside the Earth's processes. For that, what we have to do? First, we have to have we have got lots of software. Again, development of software also needs lot of interdisciplinary science. Maybe you need geology, you need geophysics, maybe you need some mathematics, maybe you need some physics, maybe you need some computer making, coding. Okay, so all these things will create a model. So once you create a model, then what happens here is you put on all the variables in this model. Then once you put all these variables in the model, you create a model, then it will tell you how deep you have to go, whether it is worth going deeper to get access to a mineral or metal or not. All these things it will tell you. I'll tell you one model which definitely gave us an advantage very recently in the geological sciences was, I know all of you heard about this uranium in Vempalli in Kadapa district. It happened in last decade or so. What happened was, it is a very classical examples of a creation of a model. Now they found out uranium, but to exploit it or to make it a mine, you have to have a good significant amount of uranium. Without that, you cannot create a mine. So once you want to create a mine, you have to show what is the value of that ore there. Is it economically viable to make a mine or not? So what happened here is they started digging and digging. Suddenly the uranium vanished. Then they said, no, uranium is not there. Then what happened here is they created a model. What happened was the rocks were dipping to one direction. When they were dipping to one direction, what happened? The uranium was strata bound between two layers of rocks. So they started looking for those two layers of rocks. They modeled those two kinds of rocks. So once they modeled everything was okay, then they could assess the continuity of this ore, how it is going, where it is going, which direction it is going, all that they could assess. That was the beauty of that model. So once that was assessed, they started drilling in that direction. They made vertical bores, and when they made vertical bores, at the first point, maybe I'm just telling you the example. At the first point, maybe they got at 300 feet. At the second point, the depth went on to 400 feet. At the third point, it went on to 600 feet. That means those people definitely knew that it was not a horizontal ore. It was an inclined ore. How they could know? Only by making a model. See, that is what is the beauty of a model. Without models, it's very, very difficult. To make this kind of a model, it's not easy. You see, you have to put in a lot of variables. You have to put in what are the kinds of rocks, if there are any faults or not. If there are faults, how many types of faults are there? What are their direction? All that. I'll not go deep into those subjects. I'm just telling you how a model is very, very important, how to make a decision. So this is what is very important. Now you see, the other part is, the groundwater pollution. In groundwater pollution also, there are so many models, so many softwares are available to model. Okay, this arsenic problem is very rampant in West Bengal and Bangladesh, because the arsenic came. I'll tell you what happened. The arsenic came from the sediments, the recent sediments which were carried along the Ganga. Still now they are not able to find what is the source of the arsenic, but they know what is the reason for arsenic in this groundwater. The reason is there is a lot of the fresh sediments were just deposited in many of these deltaic regions. Because of this fresh sediments, there is a little bit of arsenic in these fresh sediments, and this arsenic dissolved in the groundwater, thereby creating havoc in many parts of the West Bengal and Bangladesh. So what's happened was, they started trying to know what is the model. They came to know that arsenic is the culprit which is causing all these problems, the human problem, that is health problems in groundwater. Once it was known that arsenic was the problem, then they started trying to modeling it. How they would try to model? First they would try to get the hydrogeological data, that is how the groundwater is there, what is the flow velocity, what is the direction, how it is going, what is the pre-monsoon condition, what is the post-monsoon condition. Then the second variable was geophysical, resistivity, how it was going, seismic and resistivity both. Third was geochemical. Geochemical is isotopic data. Isotopic data means you get a lot of tritium you can apply, you can get tritium data, then trace element chemistry, all these things. So all these variables, these are all called variables. All these variables were put together and they made a model. And once they made a model, it was very clear and pertinent. Wherever the fresh sediments were deposited, there was arsenic problem. So this is one kind of a model again. So what they did with this model, they tried to tell us where new wells have to be drawn, where water can be drawn, where are the new bore wells to be dug. So where could be the less concentration of arsenic, where it could be more concentration of arsenic. This is one model. You see, this is what is called as a research model. So this research, unless and until you have a research model, you cannot help the society and other things. Again, you see, what is the agenda for basic? You see, you have lots of techniques for deciphering the geological reward. Terrestrial change, how it is happening. What are the extreme events? Extreme events means, these days, what is called as urban flooding. Earlier, there was what happening? There was only flooding at some places. These days, what's happening? The rainfall is there. It is like downpouring. Whatever rain has to be happen, it is happening in a couple of hours. After that, there is no rain. These are called extreme events. So you have to know why it's happening. You can create a model. Then you have to know, the second is you have to observe the active processes which are happening on the present day. Then you can deduce what happened at the geological past. So this is all about the other things you have to know and talk about. Then what you see, we have some virtual laboratories also. Once we have virtual laboratories, you can create on a computer virtual laboratories. We can do experimental research also. That means experimental research means how a rock, what happens to a rock at high temperature, high pressure, to what mineral it changes. Will it be the same mineral? Chemically it will be same, but physically its crystal lattice changes. So this is called as experimental lab, virtual lab. Once you create this virtual lab, then also it's very interesting to know what's happening deep inside the earth, because we have crust, mantle and core. Crust has got different types of rocks, mantle has got different types of rocks, core has got different types of rocks. So to model this, it requires a lot of physics and a lot of chemistry. So this is another kind of model. And I will say these models are not only important in the geological processes. I'll tell you, suppose you talk about the climate change. You know what's happening when it is rainy season, or when it is hot summer season, or all the seasons. What we do, we sit in front of a TV and look for the weather news. You say today, they'll tell us today it's going to be very hot day. Why? Because they create a model. these hot winds are blowing from Saudi Arabia, so you are getting lots of winds in this direction, so it could be one of the hottest day, and the temperature may touch 46 degrees centigrade in Hyderabad. How do they tell us? By creating a model. So you see, this is what is called as a conceptual model. How do they create a conceptual model? Taking into many aspects: evapotranspiration, temperature of the previous day, then the moisture content in the air, then what is the, how are the clouds, whether they are clear or not, what is the wind speed, what is the wind direction. Then all these aspects, once they feed, they'll get something called as a model. They'll show us the model. Whenever there's a cyclone, what they do, they'll show us what is happening in the cyclone, where is the eye, how it is moving, where does it touch the coast. All these are models, research models. Without these research models, it is very difficult for us to understand. So in every part of science, whether it's climate, whether it's weathering, whether it's tectonics, whether it is biology, whether it is zoology, whether it is geophysics, whether it's physics, whether it's chemistry, everything needs modeling. Whether it's applied science means engineering, everything needs model. Without model, it's very, very difficult for us to understand what's going to happen. So climate change definitely requires lots of models. You see, that is very important. Now, how we are going into we are going to get more and more better results. Why? Because we have got a lot of advancements in the techniques, or we have a lot of advancements in the instruments. Earlier we had some microscopes which we could not see. Now we have different types of microscope, what is called as SEM, scanning electron microscope. Then we have TEM, thermal electron microscope, atomic force microscope. What is happening with these things? We are getting more and more of data, variable data. Once we get more and more variable data, we are ready to use them. Once we are using them, we are getting more and more better results, good models. With good models, we are able to predict more accurately, more precisely. Not only that, in spectroscopy also we have got lots of instruments like AAS. We have got X-ray spectroscopy. Then we have got high resolution magnetic and acoustic imaging systems. You see, that is what I told you. Each of these sciences are interrelated. These instruments are developed by the physics people. They are altered by the chemistry people, ultimately used by an earth scientist or a environmental scientist or anyone who is requiring that. So all these are interrelated, because with the advent of these instruments, what's happening, the models are becoming more and more valid, more and more realistic. More realistic models means better analysis, good result. So that is what is happening here. So this is what we talk about isotope geochemistry. Now you see, many of you have heard about GIS. What is GIS? Global Information Systems. What is it? It is not a science, it is a tool. It's a tool to create a model, without which we cannot do any modeling. Modeling has become easy using GIS. You see, GIS can be used, I believe, in any part of science, especially earth sciences are using GIS to their maximum extent possible. So what does this GIS tool do? It creates models. To create a model, you have to put in variables. What kind of variables? Chemical variables, then physical variables. Physical variables means, you see, you can use ground penetrating radar data, you can get those things. Seismic data, you can put in those things. Then you can put some geochemical data. Maybe you are looking for some water quality, you can get some water. Then you can put in the water depth, what is the water table depth, what is the chemical parameters. Then you can create a model. All that, this modeling is absolutely easy. Most of the students these days are using, you see, these models. Without models, what is happening? It becomes very, very difficult for us to understand what's happening. Now, the other big challenge once we are into this modeling here is, the data has become so numerous and it is so vast. The data is so vast and so vast and so vast that it is becoming difficult to use. Because of that, we talk of big data. What is this big data? Because we are getting a lot of data. Because these days, you see, we have computers. You give some variables, it gives us a lot of data. But how to use this data? How to create a model using this data? that should be definitely handled by the big data, artificial intelligence. These two things are going to play a very significant role in creating future models or better understanding of the science. So big data is coming up very in a very, like I say, aggressive way. Use of big data, use of artificial intelligence into science. Earlier, I also thought that this big data and all these things are only applicable to the other only a few parts of sciences, but it is applicable to every part of science. You see, one thing I'll just show you in earth science how big data is important. You see, many people know that magma crystallizes to give rocks. That is what is one kind of a rock called basalt. Okay, yeah, I'll just show you. Where is that? Yeah, this example, you see, what happened, these basalts were classified based on Pierce 1976 classification. Now these basalts are very important in the oceanic areas. Maybe we talk about, they are basically based on basalt tectonic settings, like they are island arc basalts or oceanic ridge basalts. So this is all what's happening. How they were classified? Based on their chemistry, they were classified. Based on the formation of the magma depth, they were classified. So how they were formed mechanism, maybe they are formed by partial melting or total melting, or they are formed at subduction plate. All these things that we used to draw as geology students. We used to draw it, like we had some graphs we used to calculate and put those things, and we used to get a model how this model is there. But of course, what happens as science progressed, because of these instruments, we got a lot of data. Once we got a lot of data, the models became confusing, because it was showing in 2 or 3 different source of origin or source of formation. It become very confused. Now, why it got confused? Because the data was so much that we are not able to understand what's happening. Then what happened? They started using what is called as this rock lab or met lab. It was a totally different kind of a software, wherein they fed the data and they got the result. So this is how we got. So big data, what it is doing? It is doing large volume of data. So it can handle large volume of data, different types of data it can handle, low value density also it can handle, rapidity and time efficiency, all these things can be handled. So this creation of model is very, very, very important. To just conclude my talk, I would just try to show you one model, like what's happening here. I'll try to show you one more model. I think I have got that. Just give me a minute time. Yeah, I'm just coming.
Not that easy, but Grammarly can help.
Yeah, I try to show you one model. It's really interesting. I don't know whether I can show you or not. A Chrome tab, yeah. Yeah. I think you can enjoy this video.
Our Earth is 4.5 billion years old and has changed immensely.
I think you are able to see this video.
Humans, as we know them, have changed
You just
immensely
see here,
too,
it's a
although
very
we have
small
only
video.
been around for a
How it is
fraction of the
showing.
time the Earth has, around 50,000
I believe
years
it's also
in
a
our current
model.
recognizable state. In that time, we have left a bigger mark than any other
You
species.
see how Earth looks
How big will that
like after
mark be in the
in 1
future,
million
and will
years.
humans still be the dominant species in a million years? Hello and welcome back to Life's Biggest Questions, the channel that looks to answer exactly those. I'm Rebecca Felgate, and today we're imagining the future as we ask, what will the Earth look like in 1 million years? Of course, asking such a vast and far-reaching question is almost unfathomable. The real answer is we can't begin to imagine, but let's start with what we know and then move into a few predictions. In 1 million years, the landscape of the Earth will look different. Before the continents as we know them now formed, a larger landmass existed called Pangaea. This eventually broke up into the 7 that we now know today. As tectonic plates are constantly moving, there will be some
So this is how our
drift over the next
different
million
plates are
years.
moving.
Although it isn't really a huge amount of time in terms of geology, so the changes in theory wouldn't be too vast. What will be a vast change, however, are global sea levels. We have no accurate idea how climate could change in the next 1 million years. However, we do know now that sea levels are currently rising, and in 1 million years, it is likely that many cities will be underwater, including New York, Dubai, and Sydney. Maybe we'll find a way to adapt to that, who knows? But right now, a key part of modern life, electricity, doesn't play too well. The new high levels of water could make way for vast icy plains. Of course, if global warming continues, then Antarctica, Arctic regions of Russia and Greenland could become hospitable, freeing up new land for settlements as parts of old continents are lost, such as the future eruption of Loihi in Hawaii. On a slightly less grand scale, Niagara Falls will have completely eroded away into Lake Erie, and the meteor crater in Arizona will have eroded too. It is not just the landscapes that will change in the next million years. Time will change too. Lunar tides decelerate the Earth's rotation, which means in 1 million years, 20 seconds will need to be added to the clock every day. Okay, so here comes the big question, and believe me, it is a question rather than a certainty. Will humans still be around? So far, there have been 5 great mass extinctions on Earth, the first of which was 439 million years ago and killed 86% of life on Earth. It is a very real possibility that we will
I think
all
I'll
be
just
dead
stop
in a
here. I
million
just
years,
wanted
be
to
it
show
from
you how
war,
it happens.
worldwide pandemic, an anoxic event, or
Yeah, I'm back here. So I think I have just finished my presentation. If you have anything, I'm ready to interact now.
Yeah, hello.
Yeah.
Yeah, now the session is open for the questions. All the participants are requested. If at all you have any questions, you can ask Dr. Srinivas directly. While we are waiting for participants to ask some questions, I would put my personal kind of research experience with respect to models and all those things. And I don't know if at all it is possible during my sessions. I would like to show you all that how modeling can be done. We do lots of climate model. We call it as impact of climate change on species distribution, range extension, and range contraction, etc., etc. So that is something wherein we are looking at what is the impact of climate change, future predicted climate change on the species ranges, etc. So wonderful results come out of these kind of predictive modeling studies. So as Dr. Srinivas was mentioning, it's one of the very, very important kind of tool which is helpful in doing predictive studies. In fact, we don't know what exactly would be the result, but when we are putting in different variables, basing on our experience that we have seen in the past, we can predict the future. That is the whole idea about modeling. Research modeling is all about. Yep.
Yeah, I think you can be close to the result. Once you get better and better
anybody to ask questions.
Yeah. you get a better model by having a correct set of variables and correct set of data for the variables. You can get a very good model.
Yeah, and I don't see that anybody has any particular question as
it's
such.
okay.
But yep. If that is the case, then I would request one of you to propose a formal vote of thanks to Dr. B. Srinivas, who has given us information about research models. One of the participants. Please come forward voluntarily, or else I'll be calling names and we'll come to know that, some of you are. Okay, is Dr. Tadakamalla Srinivaslu there? Dr. T. Srinivaslu?
Yes, sir. Hello.
Yeah.
Hello,
Dr.
sir.
T. Srinivaslu, please go ahead and propose a formal vote of thanks to sir.
Hello. Hello, sir.
Sir, please go ahead, sir. Hello.
Yeah. Arvind Tirumala, are there any predictable? Are there any predictable things about earthquakes?
Yeah, please unmute yourself and speak, sir.
Yeah. No, I'm just reading a question at the chat box.
Yeah.
I'll answer just a minute. Can
yeah, while Dr. Srinivaslu will come and
Yeah, just I wanted to go to this chat box and answer this question. Arvind Tirumala is asking, are there any predictable things about earthquakes? As of now, earthquakes are not being able to predict. Okay, that is only the next to impossible thing as of now, because we don't know what's happening deep inside the earth. Creating variables from deep inside earth is very, very difficult. We know what's happening only on the superficial level or just shallower depths. So it is becoming very difficult to predict earthquakes. Earthquakes emerge from greater depths, so it's very difficult to predict. Modeling earthquakes is very, very difficult as of now, because the variables what we are getting are not sufficient to create a model for earthquakes. Yeah. Yeah.
Hello.
So I think.
Yeah, Srinivas sir. Okay, I don't know whether Dr. Tadakamalla Srinivaslu is able to take it or not. My message. Dr. Aravinda, can you please do the honors, madam?
Sir, am I audible?
Dr. Aravinda? Yeah, please go ahead, madam.
Sir, am I audible, sir?
Yeah, you are audible.
Thank you, sir. Good afternoon, one and all. Especially, I would like to thank Sir Professor Srinivas Garu for his scientific approach. Sir, good morning, good afternoon, sir. Sir, we are extremely thankful about your research on scientific approaches and inductive and deductive approach also, sir. And while you are explaining about the comparison of reliability and validity, it's a most wonderful thing, sir. You have explained very well about that, and types of models and how they are useful around in interdisciplinary things, sir. You have emphasized about the minerals and techniques, weather reports very well, sir. We are very much thankful for listening to you, sir.
Yeah, thank you,
On
thank you,
behalf
madam. Thank you for your kind words.
of all the
Thank you, Dr.
participants in
Srinivas.
HRDC,
Yeah.
I express my gratitude to listen to you, sir. Thank you so
Thank
much,
you.
sir.
Thank you, madam. Thank you. Thank you to the course coordinator, Dr. Srinivas, who is a very good friend of mine. And also thank you to Professor Srinagesh, who is the director HRDC, for giving me an opportunity to speak to
Thank
you
you,
and
sir.
interact with you. Thank you. Thank you. Have a good day.